Okay, so having discussed the philosophy of why it's good to fit the data with a constraint model, let's now talk about the mathematics, the mechanics of doing so. Okay, so, now even though we're in the transformed linear space where the weight vector is W tilde, I'm going to not put the tilde anymore, to just save a little bit of confusion and notation. Okay, so our hypothesis is W transpose Z, and we have the budget constraint W transpose W less equal to C. Okay. And we're trying to minimize the in-sample error subject to this budget constraint. So we have the in-sample error of W is 1 over n, Z W minus Y transpose Z W minus Y. Okay. And if we didn't have the budget constraint, let's say that the solution is W lin. So I'll call this the linear fit without the constraint, and this is equal to Z pseudo inverse Y, which is Z transpose Z inverse Z transpose Y when Z transpose Z inverse exists, if this exists. Okay, and that's great, and that's nice, that's the pseudo-inverse algorithm, but that's not what we want, because, we need to minimize the in-sample error subject to the constraint. So we have an inequality constrained minimization. So this is an inequality constrained minimization. Okay, and in general, those are hard problems, but in this case, this problem is manageable for a bunch of reasons. First is the linear model, so we can manipulate it. Second, this error function, the in-sample error function is a convex function, and so that has all kinds of nice properties. And so let's go and try our best to solve this inequality constraint minimization, and we'll make a lot of progress. Okay, let's sort of denote the solution. So the optimal constrained weights are W reg. So reg for regularized. So think of regularization now as synonymous with constrained, because I'm constraining your ability to fit by giving you a budget. So regularized means constrained. Okay, now let's examine the first case, which is easy. Okay. So the first case is that, your optimal linear fit, W lin transpose W lin. So your optimal linear fit satisfies your budget constraint. So this is case one. So the optimal linear fit satisfies the budget constraint. Well, in this case, I can solve the constraint problem trivially. Okay. In this case, W reg is equal to W lin. Why? Because, you cannot get any weights that are better than W lin, and they satisfy the constraint. So the optimal weights satisfying the constraint cannot do better than W lin. Okay. So the first thing you do when you face such a problem would be to check if the unconstrained solution would work for you. If it would work for you, you're done. But, odds are it's not going to work for you. If you put any kind of a serious budget constraint in order to control overfitting, okay, then, that the whole idea is that this unconstrained fit is just wild, and it's the constrained fit that's, that's different from the unconstrained fit that's giving you benefit. Okay, so the second case is that the linear fit is not satisfying your budget constraint. Okay, so let me draw you a picture of what's going on. So let's imagine that this is the origin of your space, okay, and your budget constraint, basically, the weight constraint W transpose W less equal to C is basically, defining a sphere of radius square root of C. Okay, so I've defined a sphere of radius square root of C. Okay, so this is the square root of C. Okay, and this sphere of radius square root of C is called the feasible set, the feasible weights that satisfy your budget constraint. And this guy, the linear fit, is outside your feasible set, so it's somewhere here. Okay, now, what's nice about this error function, well, what we know for sure is that this error function, this in-sample error, is minimized here. And as you move away from this guy, the in-sample error is growing. And in fact, because this is convex, the way it's growing is very nice, that this is a unique, minimum and so on and so forth. Okay. In fact, this is much stronger than convex, it's quadratic. So if I were to look at what are called the contours of constant in-sample error, it's minimum here. And then, there's a region of the an elliptical region around this linear weights, okay, where you have a constant in-sample error, and then, if you move further away and further away and further away, okay, you get, the in-sample error is increasing as you move further away. So this is the minimum, then you get larger in-sample error, larger, 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 larger. And the idea here is that on this contour of constant in-sample error, okay, the in-sample error is constant along a contour, and as you move away, it's increasing. Okay. Now, just an important fact from calculus is that, okay, if I look at the gradient, so let's say I take a point on this contour, okay, and if I move the weights along the contour, there is no change in the error. So that means that the gradient of the error along the contour is 0. Okay, so if the component of the gradient along the contour, the surface of constant E in, the gradient along the surface of constant in-sample error is 0. So that means that the gradient of the in-sample error is always normal to the surface of constant E in. And that's a fact, that the gradient of a function defines the normal to the surface of constant value for that function. Okay. Now, let's see what's the basic idea. So I can choose any weights I want inside this feasible set. Okay, and here are the minimum weights. So the basic idea is that I might try to choose. The basic idea is that I should try to choose weights that are as close as possible to the linear fit, because then I'm moving moving down the contour hierarchy and getting onto contours that are lower and lower in sample error. So let us suppose, that I pick this weight. Okay. Could that be optimal? No, because look, if I move closer to the in-sample, to the linear fit, I move from this contour to a lower contour, thereby decreasing the error. So this cannot be the optimal. And in fact, you can easily convince yourself that no weights on the interior of this sphere can be the optimal fit to the in-sample error, okay, modulo this constraint. So what we conclude is that, the optimal solution that we're looking for has to lie on the surface of this sphere. So we will keep moving closer until we get to the surface and cannot move closer anymore. So here's a potential solution. Okay. Now look at this solution. Okay. And I'm going to draw another contour, a special contour. In the middle here. Okay. So, first observation. It suffices to find the minimum of this in-sample error subject to the equality constraint. Okay. So, the inequality constraint becomes an equality constraint. Okay. And so then we have an equality constraint optimization problem. Now, if you know all about Lagrange multipliers and so on and so forth, then you can go and solve this equality constraint optimization problem. Instead, I'm going to show you a geometric approach. Effectively, I'm deriving the method of Lagrange multiplier. Okay, but it's a nice geometric picture that gives you a little bit of an intuition for what's going on. Okay, so let's look at this point, which has gone as far as it can while maintaining while staying within my set. Can it be optimal? And let's consider moving now along the surface, because I'm only allowed to move along the surface, because if I'm not on the surface, I can always do better. So if I move this way, look, I go to a higher contour and I increase the in-sample error. But if I move this way, I go towards the lower contour and can decrease the in-sample error. Okay? And so the point that I'm going to rest at, which is the minimum, can never be such that the contour intersects in this way. Okay? So I will continue to move. I will continue to move in this direction, continue to move until I get to this point, okay, where the contour that touches me no longer intersects in this non-trivial way, has only one point of intersection with me. And how do we see that this is now the optimal? We see that this is the optimal because if I move this way, I'm moving to a higher contour. And also if I move that way, I'm moving to a higher contour. So the optimal has to be a point on my surface which is tangent to a contour of constant in-sample error. So the optimal has to be a point on my surface, my constraint surface, that is tangent to a contour of constant in-sample error. Okay, so the contours of constant in-sample error in red, and I'm at a point on the surface of my constraint which is tangent to that. Okay, now let's look at what's happening here. Now remember, I just told you that at this point, so on the contour, if I take the gradient, it's always, it's pointing, in the normal direction away. So this is the direction of E in, gradient of E in. Okay, and let's look at the normal to my surface, because this is a sphere. Now this can be generally, in a more general setting, I can look at the gradient of my surface. Okay, my surface, which is this surface is defined by the function W transpose W minus C equals 0. So on this surface, we have a function that is constant. If I take the gradient of this function, I get the normal to the surface. Okay. But in this particular case, we all know what the normal to the sphere is. That's one of the convenient reasons why I chose the sum of the weights. The normal to this surface is exactly, in the direction of the weights. So if these are the weights W, in that direction W is the normal to the surface. And what do we observe? That if you're at an optimal, the gradient of the in-sample error is in the negative direction of the gradient to the surface defining the constraint. In this case, is in the negative direction of W. Okay. So what does that mean? That a necessary condition for being at an optimal is that the gradient of the in-sample error is proportional to minus W. In a more general setting, this would be replaced by minus the gradient of the function that defines the constraint surface. Okay. Proportional to means it's equal to some constant times that. So let me introduce a constant lambda sub c. Okay. Sub c because it depends on c. Okay. And I will write this as the gradient of the in-sample error is equal to minus lambda sub c times W. Where lambda sub c is, now if you're familiar with Lagrange multipliers, lambda sub c is called the Lagrange multiplier, and it has to be positive because they're in opposite directions. So lambda sub c greater than 0 is known as the Lagrange multiplier. Now, I won't discuss the general theory of Lagrange multipliers and what to do if you have more than one constraint and so on and so forth. But in this example, the geometric intuition suffices. Okay. But for mathematical convenience, I can any constant times this will suffice. So I'm going to put a 2 in here just for mathematical convenience. Okay. So if it was true with some lambda sub c, it's certainly true with, taking half of that and multiplying by 2. Okay, so this is a necessary condition, okay, for us to be at the inequality constrained minimum error solution. Okay. So that's a necessary condition for us to be at the minimum error inequality constraint solution. So this is a necessary condition. Must be satisfied. Okay, this is E in of W. Okay, let's see where that mathematically leads us. So where does that lead us? Well, let me take this to the other side. So the gradient of the in-sample error of W plus twice lambda sub c W is equal to 0. And I observe that twice lambda sub c W, this is exactly the gradient of lambda sub c W transpose W. And what this means, so in the more general setting, I would have a gradient here, but now I've replaced the gradient here because this gradient is exactly that. Okay. Think of this as W squared, so it pulls down a 2 and then you get W. Okay, so we have, and since the gradient is a linear operator, the gradient of the in-sample error plus lambda c w transpose w, that must equal 0. And so that's why we put the factor of 2 in here. It just makes it less ugly to have just this one constant here. If we didn't have the factor of 2 here, we'd have a 1/2 here. Okay. And, what do we observe about this equation that we have derived? We're claiming that if you're at a solution to your constrained error minimization, then it must be the case that the gradient of this function should be 0. Okay? But if the gradient of this function should be 0, then that means, both of these are positive functions. If the gradient is 0, okay, then that means that this function in here is minimized. So E in of W plus lambda C W transpose W is minimized. That's where we wanted to go. Very interesting. Okay, so let's summarize. So we're looking at the second situation where the solution is not trivial. So let's summarize. So we started with an inequality constrained minimization, and we played all of our, magic with the geometric view and so on and so forth. And we have come down to an equivalent condition. So this is minimized if something else is true. And what else is true? This is minimized if this guy is minimized. So this guy, this problem is solved if the following problem is solved. Minimize E in of W plus lambda C W transpose W. Minimize this guy. Okay. Subject to what constraints? No constraints. No constraints. So this is an unconstrained. So unconstrained minimization. Much more convenient. Okay. Unconstrained minimization. So we started with a constrained minimization, minimize the in-sample error subject to this constraint, and we have now reduced it to an unconstrained minimization. Except that, when there's no easy way to decide what lambda c should have been. So you gave me c, let's say c equals 1. Well, that means that there's a corresponding lambda c, the correct Lagrange multiplier that corresponds to c equals 1. So lambda sub c, the only catch is that lambda sub c is a function of c. And let's see if we can understand the sort of high-level dependencies. So what is this lambda sub c doing? When we go and minimize this in an unconstrained way, so we try to minimize this guy, try to minimize this guy. This guy is encouraging the weights to be small. So the larger lambda sub c is, the smaller your ending weights will be. Okay? Which means that you will satisfy a smaller budget. So when lambda c goes up, that corresponds to c going down. So if you decrease your budget here, you will correspondingly have to increase this guy c. If you increase your budget, you will decrease this guy c. If you send your budget to infinity, this guy will go to 0. Okay? But the catch is that, yes, I have to do an unconstrained minimization, but I don't know what lambda c is, because it depends in a very complicated way, typically, on c. Okay. And so it appears that, we have translated, we have sort of exchanged an inequality constrained minimization for an inequality constrained minimization for an unconstrained minimization, but with some unknown parameter lambda c. So we're not going to be able to do this anyway, except things are much, much better than they look. Okay. And why? Okay. Except, remember what C was. C was the budget. C was the budget. Who got to choose C? I got to choose C. I said that I'm going to do my fit in a constrained way using, modulo a budget of 1. Well, if I get to choose C, that's equivalent to me getting to choose lambda sub c. Now, it is true that there's no nice intuitive interpretation of lambda sub c as a budget. I'm giving you a budget of weights. But you can equivalently view it as, oh, I'm placing a penalty on the size of the weights instead. Okay? So rather than giving you a budget on the weights and choosing C, I can choose lambda sub C and view that as a penalty that you're going to pay that depends on the size of the weights. Okay? And instead of doing an inequality constrained minimization, I'm going to do a penalized minimization, but it's going to be unconstrained. And because I get to choose C, well, I might as well, forget about now that world with, my constraint hypothesis set H sub C, and instead just choose lambda sub C. Choose the amount of the penalty. So since C was the budget, I got to choose it. So I might as well equivalently, I can choose lambda sub C and do unconstrained penalized minimization. Okay, so now I've exchanged. So I would still have to choose C, and equivalently, I still have to choose lambda sub C. I don't need to know the mapping from C to lambda sub C because I can just forget about that world now. That world was brought in to justify the fact that if you have a constrained hypothesis set, okay, then if you fit with this constrained hypothesis set, you're going to get better generalization, and so things are going to be better out of sample if you can fit well in sample. What we have done is we have said, well, that's equivalent to, instead of picking a constraint instead of picking a budget constraint, just pick a parameter lambda sub C and do a penalized optimization. And in the back of your mind, you have the sort of comfort of knowing that lambda sub C corresponds to some C. We just don't know which one it is. And we do know that lambda sub C going up corresponds to a smaller C, and lambda sub C going down corresponds to a bigger C. So in that sense, we have sort of a principled way, a reasonable way of picking this guy. If we want to add more constraint, we send lambda sub C large. If we want to add less constraint, lambda sub C small. Okay? Okay. So, conclusion. Conclusion. Fitting under a constraint, i.e. budget, corresponds to, i.e. budget C, corresponds to penalized fitting with a degree of penalty with the penalty parameter and this is unconstrained. And now let's just call it lambda. Okay, so we don't need to even emphasize that there's in the background a budget C to which this lambda sub C corresponds. We can just call it lambda. So minimize the augmented error. So we call this the augmented error. Unconstrained minimize the augmented error, E aug of W, which is E in of W, plus lambda W transpose W. Okay. Now, this is the mathematical prescription that is equivalent to fitting the data under a constraint. Okay. Now, just for practical consideration purposes, okay, it's useful to divide this lambda by n. Okay. And that's because, typically when n is larger, you can afford to have less of a constraint. So what this account, and typically the behavior is linear. Now, I can always do this because lambda is a parameter I get to pick. So let me just pick lambda over n instead. But what this does is it makes lambda more stable across different data set sizes and so on. And the idea here is that, if you want to penalize less when you have more data, give yourself more freedom, then, you should choose lambda smaller when you have more data, and this accomplishes that. So this is just a mathematic. It's without loss of generality, but it makes practical sense. Okay. This is called the augmented error, and you will notice what we have accomplished. The augmented error, which we're going to minimize instead, which corresponds to minimizing under a constraint, the augmented error is exactly equal to the in-sample error plus a penalty term which depends on W. Plus a penalty term which depends on W times lambda over N. You can think of this penalty term that depends on W as penalizing the complexity of the hypothesis, because now remember, go back to those Legendre polynomials. You know, the larger the weights you have, especially on higher order polynomials, the more complex the hypothesis. And so here, if we define the complexity of the hypothesis by the sum of the weights squared, so by how much of each of your individual modes of Legendres you have, if you define that as the complexity of the hypothesis, then here we're penalizing the complexity of the hypothesis. Okay. And in a more general setting, not linear models, we could define the augmented error of a hypothesis H as the in-sample error for the hypothesis H plus some lambda over N, okay, times omega of H, where omega of H penalizes the complexity of the hypothesis. Okay, so in this setting, our complexity penalty for a hypothesis was W transpose W. Okay. Just some notation. This guy here, and W transpose W is called a regularizer. Okay. And this guy here, lambda, is called the regularization parameter. Okay. The regularizer, we get to pick. The regularization parameter, we get to pick. Now, weight decay is one of the most popular regularizers. Okay. And there are other types of regularizers, Tikhonov regularizers, this regularizer, that regularizer, and so on. So there are some standard regularizers. And so the recommendation in practice is, pick whatever standard regularizer you want to pick in order to perform this, penalized minimization, this constraint optimization. So minimizing the in-sample error under a constraint. Okay. The regularization parameter, however, is a real parameter that you have to pick. So we don't exercise too much freedom in picking the regularizer, but we really have to pick, we have to decide how much constraint we want to put on the fitting, and that means we have to decide how much to turn this regularization parameter knob. So you can view this lambda as a knob to turn that dials up or down the complexity of the final hypothesis that you produce. And now we can compare this with the VC theory, which said that E out of H was less equal to E in of H plus omega of big H. And we have succeeded in our sort of high-level plan of replacing the sort of penalty for the hypothesis set with a penalty for the hypothesis. Okay, fantastic. All right, so we did all this intense derivation and we reduced regularization to a mathematical formulation of penalized in-sample error minimization. Let's see if we can actually get an algorithm, a concrete algorithm for linear models. And it turns out we can get a concrete algorithm for linear models. I'll do that derivation quickly. Okay. And, then hopefully we have saved some energy to see regularization in action, in practice. Okay. So, linear models and weight decay. So we're going to derive now a concrete algorithm, and within the context of linear regression, so you can easily implement regularization. And then if you use regression for classification, you can use the regularized regression for classification, and it should give you a more robust regression for classification, a better starting point for the pocket algorithm, for example. Okay, now, so the prescription is to minimize the in-sample error plus lambda over n times the product of the weights. Okay, and we get to pick lambda now. We've forgotten about the background world in which we have a constraint, a budget constraint, and we're optimizing. We're just doing penalized optimization where we get to pick lambda. So pick lambda, and we'll discuss that a little bit. and minimize E in of W. So E in of W plus lambda over N W transpose W, which means what we have to minimize, 1 over N Z W minus Y transpose Z W minus Y plus lambda over N W transpose W. And now I'll do this quickly because we've seen derivations like this many times. So this means that we need to minimize. Okay, the 1 over N can be ignored, so minimize Z W minus Z. So W transpose W, W transpose Z transpose Z W minus twice W transpose Z transpose Y plus Y transpose Y plus lambda W transpose W. So this is equal to, minimize W transpose Z plus lambda I W. So here's W transpose Z W, and then here's W transpose times lambda I times W gives me this term, minus 2 W transpose Z transpose Y plus Y transpose Y. And we take the gradient of this and set it to 0, we get the regularized normal equations. So we want that twice Z transpose Z plus lambda I minus twice Z transpose Y equals 0. And when we solve this, okay, assuming now, typically, this is positive semi-definite, but this is positive definite. So now this is always invertible. So that's another advantage of regularized, of the regularization of the regularized linear model. Weight decay, by the way, is just referring to that regularizer, the norm of the weight squared. So this guy is always now invertible. Okay. So that regularizer, this W transpose W, makes this in sample error minimization. It always makes it stable. Okay, so solving for sorry, I left out the W here. So this is W squared. When you take the gradient, you have W. Solving for W, you get that W is equal to Z transpose Z plus lambda I inverse Z transpose Y. Okay. And so this we call W regularized. Remember, W lin was very similar, except that you can recover W lin by setting lambda to 0 if this is invertible. So W lin was Z transpose Z inverse Z transpose Y, which corresponds to lambda 0. Okay. So this is regularized linear regression with the feature transform. Okay, so let's pass all those words. Regularized, so you have regularization, you have this penalty term, and you get to pick how much of the penalty term to have. And the more you pick, the smaller the resulting weights, because you're penalizing complex weights, you're penalizing large norm weights. So this corresponds to complexity being defined as the norm of the weights. Okay, so this is where the regularization is. You get to pick how much regularization, the knob, to turn up or down. Okay. Feature transform, because we're in the Z space. Okay. And so we can do regularized regression in the Z space. Fantastic. Okay, so let's erase. And now let's move to some experiments, and I'm going to show you regularization in action. And we'll use the slides.